All right, guys, so welcome back. This is the force and energy review video. So I'm going to go through the answers on how to complete the review for the Unit 2 test. The first page I'm skipping because it's all really just definitions and equations and understanding units and things like that. So that's all found in the notes, so you don't really need any instruction for that. So starting with the back of the first page, it begins with an action-reaction pair. So it says label the action-reaction pair in the picture here. So I'm going to go ahead and start to do that. So for the action, I would say the two, remember for an action-reaction pair, you need a pair needs two things. You have two objects, a verb, which is either, your verb is either pushing or pulling, and then you need directional ideas, up, down, left, right, whatever it is, okay? So it's just switch and flip. That's the way to get this right. So if you just switch and flip, you're going to get it. So I'm going to say the foot pushes the ball going up, because that's the way I think the ball or foot is getting kicked by the ball. And then it's just switching and flipping. So we're going to switch the two verbs. I'm sorry, switch the two nouns. So the ball pushes the foot. So we switch their positions, and then we're going to flip the direction, which is down. So it's the arrow's going to point down here. So that's an action-reaction pair for that picture. For the next set, we're dealing with Newton's third law. This is part of Newton's third law, is action-reaction pairs. But we're going to talk about the three laws and explaining why you think the law is related to the statement. So the first one says to cause the same acceleration for an empty and a full shopping cart, you have to push a full cart with more force. So, I'm going to say this is the second law. The second law is the net force is equal to the mass times acceleration, or if you rewrite it, it's A is the net force, or sum of the forces divided by M. So with an empty cart, the mass is smaller. With the full cart, the mass is bigger. So in order to have it have the same acceleration, if you have a bigger mass, you're going to need a bigger force to make that stay the same. So, but it's dealing with the ideas of F and M and A, so that's the second law. The next question or statement says the computer does not move by itself, so it's not moving, so it's at rest and staying at rest. So if it's rest and staying at rest, I would say that's the first law, Newton's first law. It also deals with objects at a constant velocity, and they do that as long as the net force is zero. So this is a net force zero situation or balanced situation. If they're unbalanced, then it does accelerate, and that would be the first law as well. Process elimination here, this should be the third law for action-reaction pair. So it's like you're swimming, you push your arms, push the water backward, but the water pushes you forward. So again, the directional idea makes me think of action-reaction pairs with the equal and opposite forces. Okay. So this first page is mostly conceptual. The last of it is talking about explaining how changing the mass or separation between masses in Newton's universal law of gravitation would affect the forces. So first you need to know the universal gravity equation, which is this one. So it's Fg, the force of gravity, is equal to the universal gravitational constant g. That's just a constant. M1 and M2, those are masses. And then R is this idea of separation. So we're talking about how the force of gravity changes with these ideas changing. So again, I talk about often in class the idea of direct and indirect relationships. So if anything in the numerator gets bigger, then this numerator over here in the same part, gravity would get bigger. So mass increases causes the force of gravity to increase. And we did this in the activity as well. In the opposite parts, that's called an indirect relationship. So they're in opposite parts of the fraction. So as the separation increases, the force of gravity decreases. So that's just talking about the relationships between them. Okay, so then we're going to get into the force problems. So this one says you're pushing a shopping cart horizontally down an aisle with a force of 120 newtons. If there's a coefficient of kinetic friction of 0.35, determine the acceleration of the shopping cart. So first thing you need to do is draw a free body diagram. So that dot represents the shopping cart. We are pushing it, so I'm going to say the push is going to the right. Gravity is acting on the cart, so Fg. The normal force or the floor is going to hold the cart up, so those two are going to be balanced. And then friction is going to go against the motion of the shopping cart, and technically it's kinetic friction if you want to call it that. Going through the numbers, 15 kilograms is the mass, 120, that would be the pushing force. And then 0.35 is the coefficient of kinetic friction, so that's mu. Okay, if you want to do it. We're asked to find the acceleration. To do that, we got to get through everything else. So we're going to use our table here and list out our forces from our free body diagram. So we're just listing out those forces that are in this picture. And when we add them all together, we get the net force, or sigma F, same idea. Before we get into filling in the boxes with numbers, let's fill in plus minus zero. So the pushing force is going to the right, horizontal is to the right, so that's positive. Up and down is the vertical, or the Y, so up is positive, down is negative. The push isn't going up or down, so that's going to be a zero. Gravity is not going horizontally, it's going down, so that's negative. Normal force, not horizontal, but it is up, so that's positive in the Y. And then finally, friction is going left, so that's negative horizontally, and it's zero in the Y. When I add up my Y component, my shopping cart isn't going to fly up off the surface or fall through the surface, so that's going to be zero. And we're going to do all the math to figure out the other ideas. So the pushing force, they told us that's 120, so that's going to go 120 there. For the force of gravity, we need to calculate it, so it's m times g. So it would be 15 times 9.8, which is 147. So negative 147 is my gravity force. I've determined that I need to find the normal force. There is no equation for that, so I'm going to just use the chart and say, okay, negative 147 plus a number gets me to zero. So that's got to be a positive 147. Again, all the ideas in the chart are measured in newtons, so if you want to do that to cover your units, you can do it that way. So I got 147 going down, I got a positive 147 going up, I got a positive 120 going to the right. I need to figure out what my friction is going to the left, and then I can figure out my net force. So, I'm going to use an equation that solves for friction, which is the fun equation. So force of friction, it's kinetic, I put little k's. It's 0.35 times the normal force, which is 147. If you put that in your calculator, you'll get negative 51.45. That's going to go in here. Actually, it doesn't tell you it's negative. It tells you it's positive in the calculator, but we knew it was negative because it's going to the left. We're going to add 120 to the negative 51.45, and you end up with 68.55 for the number of newtons for the net force. And then we're going to use Newton's second law. A equals net force over m, or F equals ma. You did it that way. And you're going to plug in and solve. So the net force is 68.55. Mass is 15. And A is what we're looking for. So divide through by 15. And you get an acceleration of 4.57 meters per second squared. So that's the answer to the first one. There'll be a question like this on your test. It's similar in nature to kind of drawing a free body diagram, figuring out the different ideas in terms of your force diagram with positives and negatives and zeros, filling that information in the chart, getting the numbers, doing all those things. So that's pretty common. You want to show this level of work to make sure you get full credit. Okay. The next question is dealing with some energy. So it says a 24 kilogram child descends a 5 meter high hill slide and reaches the ground with a speed of 2.8 meters per second. The system is the child slide and earth, and we're going to calculate the GP at the top, the kinetic energy at the bottom, and then C says describe the system energy change from the top of the slide to the bottom of the slide and why those things are happening. So we're going to talk about all the different energies and how they're changing. So first off, we need to label things. So mass is 24, height is 5. That's going to be my initial height. It reaches the speed at the bottom at 2.8, so that's the velocity. So it's kind of going down the hill like that. So this is my final position. So the kid on the slide and the kid on the slide going down. So this is my initial position up here. All right. For part A, we want the gravitational potential energy. So that's not too bad. It's just mass times gravity times height. We want the initial, So it's at the beginning, so it's the mass, which is 24, times 9.8 times the height, which is 5. So if I multiply all three of those things out, I get 1176 joules. The kinetic energy at the bottom, kinetic energy is equal to 1/2 mv squared. I want the bottom, so this is the final information. So 1/2, 24, and it's only going 2.8 meters per second squared. So that's going to be a value of like 94.08. So it's a smaller number. They are not equal. So there has to be some sort of other kind of energy here at the bottom that's going on. So let's just talk our way through these ideas. So gravitational potential energy. So at the beginning, it's got a lot of gravitational potential energy because it's got a height. At the end, it's got no height. So the GPE decreases because the height decreases. So that's all you got to kind of talk about for that change and understand that. For kinetic energy in the beginning, the velocity initial is 0 because it's not moving. And then the velocity at the end is 2.8. So in this case, going from that to that, the velocity increased, which would make the kinetic energy increase because kinetic energy equals 1/2 mv squared. I didn't write this in here, but GPE equals mgh, so it's a direct relationship. If h gets smaller, GPE gets smaller. Finally, mechanical energy. In the beginning, the initial mechanical energy is all the GPE to start. So that's 1176. At the end, the mechanical energy at the end is all the kinetic energy, which is only 94.08 joules. So our number got smaller, so the mechanical energy dropped, and that's good enough math. So like the kinetic, the gravitational potential energy initial is bigger than the kinetic energy final. In the beginning, the non-mechanical energy in the beginning, it's not moving, there's no heat, there's no sound, so that's 0 in the beginning. At the end, there has to be some non-mechanical energy, so it's equal to some number because otherwise this kid would be going faster. So the non-mechanical energy increased as time went by. Total energy is constant. It's always constant because of the law of conservation of energy. This is an isolated system, so there's no work being put in or out. So conservation of energy means that if there isn't any work, then the total energy in the beginning equals the total energy at the end, and that's fine. If you wanted to do it as like an LOL graph, you could do it that way. So again, I said that the child, the slide, and the Earth are part of our system. In the beginning, it's all GPE, and that's equal to the total, that bar. At the end, there's kinetic energy, but it's less. And then the total energy has no energy flowed in or out through the process of work. So those aren't the same, so we have to add that non-mechanical in. So that's where this non-mechanical bar is. So those two together would equal that. So, but these ideas of the total energy, they're equal. So the initial and the final total energies are the same. Okay, so that was question number 2. Question number 3 is our work and power one. So we're going to need the work equation, which is FD cosine theta. For the power equation, that's the work divided by the times. This is pretty similar to the power lab if you did that in person. If not, it's just kind of like using the idea with work or power and energy. So it says motor A can lift a block. So if this is A, the motor A can, it's over maybe a pulley, and it lifts this block. It lifts it upward, and it's a 10 kilogram block, and it lifts it for 4 meters. And it does that in 20 seconds. So 20 seconds is a time. That's the time I'll say for A. The mass of A on the block is 10, and then the height of A is that. You can also call it distance of A if that makes more sense to you. But and then we have scenario B, where you have a different motor, and B can lift a different block, which is 15 kilograms. And it lifts it to a height of 5 meters, so it goes taller. And as our height would be our mass of B. And it does it in 40 seconds. So we're going to basically do that kind of work and information. When you're lifting something up and work, you need a force and a displacement, or a force and a distance. So the force is going to be the force of gravity, which is just m times g. So if we do for A over here, and we do for B over here, doing math is good for showing kind of the idea. So it would be the work is equal to the force times the distance times the cosine of the angle. If you think about this, the force is pulling up and the object moves up, so F and D point the same way, so theta is equal to 0 in both of these cases. So D and F, they're pointing the same way, so theta equals 0. So cosine of 0, put that in your calculator, that's just 1. So this part of the idea just goes away. So you need the force, which is like mg, because it's the weight, times the distance for each one. So for A, it's 10 times 9.8, that's the weight, and you're going to multiply that by 4. So that number turns out to be 392 joules. So that's how much work that one does. And then for B, it's again FD, cosine theta, still just cosine of 0, which is 1. So it's m times g, so it'd be 15 times 9.8 times the height that it goes to is 5. These numbers are bigger, so it's going to have more, it's going to do more work. So it ends up being like 735 joules for part A. Part B, I'm going to erase these pictures down here, hopefully. For this part down here, we're going to calculate the power. So to do power, you take the work over the time. So for A, the power of A, this was A, this was B. So work B is greater than work A. And the explanation can just be showing the math. Okay. For power A, you need the work A divided by the time for A. So the work A is 392, and we're doing it in 20 seconds. So 392 divided by 20, something like 19.6 watts. So we calculated that. For B, same kind of math, just different numbers. So power B equals work B divided by the time of B. So the work is that 735, and we're going to divide it by 40. That only turns out to be 18.375 watts. So the work, or I'm sorry, not the work, the power for A is more powerful than B. And again, your explanation is basically just doing the calculation and showing your work. All right, so the next problem is one where we're looking at forces and kind of what's happening with free body diagrams and acceleration and things like that. So it reads a 0.5 kilogram, so that's the mass toy figure with a parachute is thrown upward from the top of a roof at position A. So we're starting here at A. You throw it up, it rises into the air, then it falls. As it falls, the air resistance changes. So it says draw a free body diagram for each position and calculate the acceleration. So it tells you about position A, so let's draw a dot to represent the forces. So at A, after it's thrown, the force of gravity is going to act. And then as it's moving upward, air resistance goes against that motion. So I'm going to have another arrow going down. So I have those two forces as it rises into the air. Those two forces make up the net force, or sigma F. So I have air, which is down, so I'll make that negative, plus the gravity force, which is also negative, and they equal the mass times the acceleration. So we can calculate the force of gravity. Let's do that. The force of gravity is not going to change. It's going to stay constant for the whole problem. So it's 0.5 times 9.8. So 0.5 times 9.8 is 4.9. So it's going down. So this one's going to be a negative 4.9. Air, it says it was -1 here. And then those are equal to the mass, which is 0.5 times the acceleration. We're trying to figure out the acceleration. So negative 5.9 equals 0.5a. So when I do that math, I get a equals, so if I divide by 0.5 or multiply it by 2, I get a is equal to negative 11.8 meters per second squared. So there is an acceleration that is pointing downward, and it's that amount. We're going to do similar work for each of these points. So this was point A. For point B, we're going to draw our picture when it's at this point. So at this point, it's falling down. At this point, it was going up. So if it's falling down, gravity is trying to pull it down, so that's Fg, and that's going to be negative because it's pointing down. And then the air resistance is going to be upward, and it's resisting its fall, so air is going up. So we have a positive force of air and a negative force of gravity. Again, we just kind of add them together. So the positive air plus the negative gravity equals m times a. For the air, it was positive 3 that was given to us. Gravity is still negative 4.9. That equals the mass, which is 0.5 times the acceleration. So the difference between 3 and 4.9 is a negative 1.9 equals 5a. Divide through by 5, or 0.5, excuse me, the mass of the object, and you get an acceleration of something like negative 3.8 meters per second squared. So it's falling down and accelerating downward, but it's not in free fall because the air resistance is trying to push up for it. Finally, for point C, this is when the parachute is fully opened, so it's going to have the most air resistance, so that's 4.9 going up. So for part C here, we got gravity pulling down, that's still negative, and the air going up. And if you notice the numbers, the air and the gravity are balancing out at this point. So if I do this, the sum of the forces, I have the positive air and the negative gravity being added together equals ma. So I have a positive 4.9 plus a negative 4.9 equals 0.5a. Positive and negative 4.9 is going to give me 0. And then the only answer that will work for this is 0. So this object at this point is 0 acceleration. And if you have 0 acceleration, that means that it's moving at a constant velocity. When something falls at a constant velocity, that's called terminal velocity. So C is the answer because our acceleration is equal to 0, so we have a constant velocity. So that's a problem that's like looking at free body diagrams, taking your free body diagram and developing tables or charts. If you wanted to make a chart with the y direction instead, these equations here with sigma f or f net is another way to write it. That's the same as doing this work. So you'd have gravity, negative, and air, which could be positive or negative depending if we're on A, B, or C. And that's equal to the net force. So it would be like negative 4.9, and then whatever this number is for the air, and then we set that equal to ma and solve for A. So that's kind of what we did with the elevator activity if you did that in person in class. All right, last one here, number 5. A child makes a ramp with a 3-meter long board to push a car up to the top. He pushes the car with 2 newtons of force and lifts the car, or the 10 newton car, excuse me, to the top of the ramp. So it says assume the situation to be 100% efficient. Okay, so we have 100% efficient. That means that the work out equals the work in. Or if we use the efficiency equation, efficiency equals work out divided by work in. So they're the same number, so that just equals 1. That means it's 100% efficient. So the child makes a ramp with a 3-meter long board. So going this way along the ramp or up the incline, that's the distance of the incline, that's 3 meters. Okay. He pushes the cart with a force, so that's his input force of 2 newtons. And he lifts this car, basically this blue car, it can go up the ramp, but if you wanted to lift it, you'd be lifting it up that way. And this is a 10 Newton car, so it's like the weight of the car. So the first question asks how much work did the student do? So work equals Ft cosine theta. The way that the car moves is up the ramp, and he's pushing the same way parallel. So cosine of that's 0 degrees still, theta is 0. So it would just be 1. So you don't really have to worry about that. So he pushes with 2 newtons up a distance of 3 meters. So that's 6 joules of work. It asks what the mechanical advantage of the car is, or MA. So the mechanical advantage would be the distance in divided by the distance out. That's one thing we can know. We don't know the distance out. Distance out would be how much the outcome is, so the car, how much the car moves up. So we can't use that one, but there's this other equation that says it's the force out divided by the force in. So the force out, you're lifting 10 newtons, and you only have to put in 2 newtons. So 10 divided by 2 is 5. So 5 is the mechanical advantage. How tall the ramp is, that's solving for the distance out. So that's going to be the same MA equation, but this time it's DI in and distance out on that side. So it'd be 5 equals the distance in is going to be 3, and we need to figure out the distance out. So again, I like cross multiplication, so 3 times 1 is 3, and then it'd be 5D out, and then I have to divide by 5. So you're going to get the distance out is something like 0.6. If you like the triangle better, the triangle would be the mechanical advantage, distance in over distance out. So if we plug into that, distance in is 3, mechanical advantage is 5, and we're looking for the distance out. So 3 divided by 5 still gets you 0.6. So again, if you like that kind of setup with the triangle, you just have to take the fraction. The top of the numerator is going to be the distance in, the bottom is down here in the bottom of the base of the triangle, and then whatever's on the left side is also in the base. Okay. So finally, kind of getting into D, it says how much work would be needed to lift the car straight up towards the top without using the ramp. Because it's straight up without using the ramp and it's 100% efficient, the work out is going to be equal to the work in. So we said the work in was 6, so the work out's going to be 6. So that's that one. Finally, it should be part E, but it says part D twice. Part E says, if there is friction and it takes the child 4 newtons to push the car up the ramp, what is the efficiency of the ramp? So really, it takes 4 newtons instead of 2. And you're gonna have to do kind of the efficiency equation again, which is the work out over the work in. For the work out, we're still getting 6 because this 10 newtons is going up 0.6, so that's gonna be 6. And then for the work in, it's the force in, which is 4 divided or multiplied by, so it's FD, force in, distance in. So 4 is our new force in, our distance is still 3. So 4 times 3 is 12, so it's 6 over 12, which is 0.5, which is equal to 50% efficient. So this is not a very efficient ramp. There's a lot of friction on it to slow the car down. Let me just talk about the test briefly before I let you guys go. So the test you're gonna have, there's a multiple choice section. There are 10 questions. That's mostly like terms, units, ideas like that. So that's fine. Kind of ideas with energies and forces and kind of what types of ideas those are. Those are 1 point apiece. So that's 10 points out of the 100. After that, you're gonna have short answer. On your short answer, you're gonna have an action-reaction pair, similar to what we did with the foot kicking the soccer ball. So you can have one like that. You're gonna have Newton's laws. So I'll give you some statements like I did right after the action-reaction pair. You're gonna have Newton's laws. You're gonna have to state and explain. So you're gonna have to say what law you think is being exemplified and explain why you think it is. So using kind of the examples that we talked about now. Then we get into the problems or the mathematical kind of solutions. There's one similar to the shopping cart one where there's a force applied, where you have to do like a free body diagram. You gotta use your chart or your equations. And then you're gonna solve for various things, FG, FN, FF, FNet. And eventually you're gonna try to get the acceleration. The second problem is like an energy conservation one. So energy, so kinetic, potential, either of the potentials, non-mechanical, and kind of doing some calculations for these, and then also, kind of ideas and qualitative ideas like what's happening to the energy. So changes in energy, what's happening to the energy. Again, similar to what we did in this review. So if I go back to this problem, but not that one, this one, the child on the sled, that's similar. Like we talked about what's happening to the energy comparing one point to another point. So again, I try to design the review so that it's similar to the test. So if you do well on the review, you'll be fine for the test. There's a mechanical advantage ramp problem. So we just did that one. That's what we just ended up with. There's a problem with free body diagrams and using the free body diagram to calculate the acceleration, so the net force equals ma. So either the chart method or using the sigma f method, but you come up with your equation and then set it equal to ma and solve for a. So similar to the toy problem with the parachute, that kind of problem. And then the last problem is more like the motors. Yeah, there it is. So the last one is dealing kind of like the motor problem with like work and power and calculating and comparing. So deciding which one has more work, which one was more powerful based on those ideas. So that's the overview of the test. Similar setup to last time, similar timing to last time. So hopefully you feel good. Again, if you can do the review, you should be fine for the test. So study the review, make sure you can do problems like that, make sure you understand why you're doing those things, and good luck on the test.